Welcome back to Principles of Statistics. In Chapter 8, we study how to create interval estimates. If you remember, we use samples to try to gauge to reach conclusions about the characteristics of the population. In particular, we want to make conclusions regarding the mean of the population or certain population proportions. If you will remember, our best estimator of the population mean is the sample mean. We are now interested in constructing intervals, i.e., ranges of numbers, such that we can be reasonably confident that the true population mean is within that interval. So please keep in mind certain notions. We can be reasonably confident, and intervals being ranges of numbers. There are several cases we will consider for constructing interval estimates for the population mean. In some instances, we know the standard deviation of the population. In other instances, we may not know the standard deviation. We will consider those two cases in constructing interval estimates. Another related topic is how to determine the sample size so that we can reach the required degree of confidence. And finally, we will look at constructing interval estimates for population proportions. Many of these concepts will be familiar and directly follow from Chapter 7. Hence, many of the procedures will also be similar. As we recall, a point estimator cannot be expected to provide the exact value of the population parameter. I cannot really say that the average height of City College students is something 68 inches, because that will probably be wrong, because that will depend on the samples I have drawn, some of which may be outliers. Hence, what will improve our estimate is if we can say the average height of City College students is 68 inches and a certain margin of error, some plus or minus inches around our estimate. So as the letters in red point out, the purpose of an interval estimate is to provide information about how close the point estimate is to the value of the parameter. This is the general form for the population mean. The sample mean plus or minus some margin of error will contain the population mean with some degree of confidence. In order to develop an interval estimate, we need to construct, therefore, a margin of error. Now, there are two ways to construct the margin of error. If we are lucky, we may know the population standard deviation, and we can use that. That is the case where sigma is known. But sometimes sigma is not known. But sometimes we can obtain good estimates for sigma based on historical data or other information. That is also considered consistent with the sigma known case. This is basically how it works. We determine alpha, and from that we can determine 1 minus alpha. And 1 minus alpha will then be our degree of confidence that the true population mean is contained within the interval we have constructed. As you will see, on the right hand side there will be a value of z, and on the left hand side there will be another value of z, which will be the negative of the right hand side. As you will see, if 1 minus alpha is in the blue shaded area, then alpha must be the areas to the right and to the left. And since the curve is symmetrical, the size of the area to the right must be alpha over 2, and the size of the area to the left must be alpha over 2 also. Now, if you will remember from Chapter 6 and 7, if we know alpha, we will know 1 minus alpha. If we know 1 minus alpha, then we know what is the size of alpha over 2 on each side. Do you remember how we will be able to determine what the magic z numbers are? Please take a minute to consider the question. This is a reiteration of the previous diagram. We can be, for instance, let's say our alpha is 0.05. Hence, our 1 minus alpha will be 0.95. We can therefore be 95% confident, depending on how we construct the confidence interval, we can be 95% confident that the true population mean will be within that interval that we will construct. This is therefore the formula for constructing the interval estimate of mu, the population mean. Mu is the sample mean. X bar, is the sample mean. 1 minus alpha is the confidence coefficient, and z of alpha over 2 are the two critical z numbers. Sigma is the population standard deviation, which we need to know in order to work with this procedure, and small n is the sample size. Please take a minute to consider the equation. As you will see, it looks familiar, doesn't it? Remember the equation z equals x plus or minus the mean divided by the standard deviation of the variable? This is basically the same equation rearranged. And please also note that sigma over square root of n is similar to the standard deviation of the sample mean, which we discussed in chapter 7. What alpha should we use? And our choice of alpha will also determine the critical z's. Typically, we work with 90%, 95%, or 99%. Consider, for instance, 90%. If the area in the middle, shaded blue, is 90%, then the area outside the blue part must be 10%. And since the curve is symmetrical, each of the two wings to the right must have an area equal to 5%. Now, if you remember, we always look at areas to the left. Hence, for the z that's on the right of the curve, if it's 5% to its right, it must be 95% to its left, which is consistent with the critical z of 1.645. Please consider this table and do this exercise for yourself. How exactly did we get the critical z of 1.960 for the 95% confidence level? Here is another way to look at the meaning of confidence. Please take a minute to read the description. The key here is that given that the variable, the sample mean in this case, is normally distributed, we know that 90% of all the intervals we construct will indeed contain the population mean plus or minus a certain margin of error. And that margin of error will be equal to 1.645 times the standard deviation of the sample mean. Here is an example. Please take a while to read the description. The key here are 2 points. First, the population is not believed to be highly skewed. In that case, because the sample size is quite large, 36, we can use the normal distribution. Second, we are given the population standard deviation, which is 4,500. Now, the choice of confidence coefficient is our own, but in this case, let's use 0.95. And if you will step back, do you remember what the critical z is for 0.95? Here it is. The critical z is 1.96. Hence, to construct a 95% confidence interval, we use the formula. And the calculation is shown as follows. So the margin of error will be 1470. Hence, we can be 95% confident that the true population mean will be plus or minus 1,470 compared to the sample mean. Or more specifically, we can be 95% confident given that the sample mean is 41,100, that the population mean will be between 39,630 and 42,570. As you will see, depending on the degree of confidence, the interval estimate will also change. That is because the critical z changes, and therefore, if we look back at the formula, when the critical z changes, the margin of error also changes. How would the margin of error change as the degree of confidence increases? As you will see, in order to have a higher degree of confidence, we have to have a larger margin of error or a wider interval estimate. It's like saying, consider this example. Which statement can you be more confident of saying? My final grade will be between 60% and 80%, or my final grade will be between 40% and 90%. You can be more confident of the second one, right? Because it covers a wider range of possibilities.